So, good morning everyone. Today I am going to discuss the tangent bundle of our configuration space. And this is a very important topic because Lagrangian mechanics is formulated in the tangent bundle of a particular configuration space of some mechanical system. And so a good insight on the geometric interpretation or the geometric definition of this object is very useful for you to keep track of what's going on in Lagrangian mechanics. So recall that last time we argued that our configuration space is going to be a parameterized manifold on a higher dimensional space, a Cartesian product of Euclidean spaces that we don't care about. And so the basic feature is that we have a set of parameters, q1, q2, qn, that allows you to identify uniquely all the possible configurations of the system, be it the position of a particle in a very high dimensional space, or be it the position of many particles in a lower dimensional space. Whatever it is, we don't care. It's just that it must be bijective with a set of all possible configurations that, as we saw last time with the example of the bead on the wire, it's very intuitively comprehended as how many possible combinations of positions of every single particle I can make. Okay? So, today, well, last time there was no physics whatsoever in our discussion, so we were just describing the geometry of the possible spaces in which our particles can live in. And so today, what I will introduce is the basic motivation of the whole of mechanics, and that is motion. So when we move in these spaces, what happens when we move in these, or how do we describe or mathematically describe motion on this space? Obviously, in three-dimensional space and Newtonian mechanics, it's what we are used, or what you're all used to, and it's three-dimensional Euclidean space. You have motion of particles as curves, and you compute the tangent vectors as a derivative with respect to the time parameter that is giving you the curve, and so on and so forth. But now we have switched to a new picture, as you will see through your journey through analytic mechanics. It's much more powerful, of considering mechanical systems in this abstract and general way of configuration spaces. So now we need to consider what does it mean to move on a configuration space. So indeed, as you can, I mean, this terminology is intentionally intuitive. So you should actually have a picture in your mind that if you say configuration space, it's actually the set of all possible configurations of the system. So if the system changes, I mean, there's a very natural definition of what change means in this context. And that is, if you define a configuration to be a point of Q, and you define a configuration as, or you imagine a configuration as being the state of the system, of a mechanical system, you know, like a snapshot of the system, like a picture of the system in a particular moment of time, then obviously change of the system, or evolution of the system, will be just a movement or a curve through configuration space. So we need to consider, I hope that, I mean, you can convince yourselves with a very specific example of three-dimensional Newtonian mechanics that is a particular case of a configuration space in which configuration space is just R3, so our usual three-dimensional Euclidean space. You can convince yourselves that moving in this particular, moving in space, as you can normally imagine evolution of mechanical systems as moving in three-dimensional space, is exactly moving on the configuration space manifold, in this case R3. Quite tautologically, but it's precisely what motivates and hopefully will make it easy to convince yourself that generalized change in mechanics or evolution of systems indeed is just curves in the generalized configuration space. So I think it's a very nice picture to have in mind. I mean, it's like you don't care about how you precisely define your coordinates as long as you do it properly. It's not that well, it's a big problem to do it properly, so you have to be very careful how you define your coordinates for particular purposes or for particular problems, but not in general. For developing the general theory is completely irrelevant as long as you assume that you have done it well, okay? So you have to actually do it well if you want to apply it for a certain problem. But if you assume that you've done it well enough, that you have a bijection in between your parameter space and your configuration space, then it's as simple as saying, well, consider curves on parameter space that will translate into the curves on the configuration space. Recall the first lecture in which we saw this curve on the space of phi and theta of the spherical parameters, and then you got mapped into a curve that laid on the sphere, on the shell of the sphere, right? And didn't go away. Okay, so it's very natural to just, even you can possibly, when the mechanical systems are defined in a more general way than are not thinking of particles moving in three-dimensional space, as evolution of a system being a curve through the configuration space. Okay, so I mean, this is just the usual calculus that you've done already, or some bit of geometry that you've done already of curves moving in spaces, right? And that's very, very much what we did in the first lecture. We had these parameter manifolds, and we had curves in these parameter manifolds, and we described them with these tangent vectors and the tangent planes and everything. And now that discussion is going to be absolutely equivalent. But the only thing is that we're not living in the 2 dimensions to 3 dimensional example. So this is a higher dimensional example. I will indeed compute explicitly a 1-dimensional example so that you can actually see geometrically all this notice, what's going on in this notice. But first, let me have a general discussion on how the tangent bundle of Q is defined and how it arises from just curves on Q, which are precisely what we understand as evolution of mechanical systems. Okay, so let's begin. So remember that we did this. There's always this map implicit. This is not, again, it's not important in application what this map is, as long as you have properly identified uniquely your configuration states and your parameters. But recall that there's a map that gives you certain into, I'm going to say yes. So I'm going to say directly Q. So, okay, so there's a set of possible parameters, which is indeed are Q1, Qn, okay, and they are mapped into a specific, I mean, this is just for you to bear in mind where we are, right? So let me have always. So this is the general picture, right? And then what we want to consider is curves moving in this space. So let me use a picture that will take. So this is parameter space Q1, Qn. This is this phi. It's not really important in practice, but it's what actually. And this is Q. Okay, and Q is a general. General surface. Okay. So this is the picture that you have in mind, and then here something very analytic. That's where this name comes from. Very analytic sort of description of your mechanical system, such as with rollers and angles, and you gauge where the particles are by just measuring distance and angles, and so this space represents that. And so we saw in the first lecture that a general curve in here, a general movement, so the system is here in some position, so that position there is a point of Q, and so that position there, it's not zooming in, there's no structure in this space, this is just a manifold. But that represents conceptually, a mechanical system that is, imagine a pendulum that is attached to spring and that has another pendulum or wherever, and then you have one angle here, one distance here, and I don't know, one angle here. Okay, so you've got many positions at a different point of configuration space. Would be the same system, right? So same pendulum, same spring, and now different spring maybe here, the other part over here, pendulum, like that. So it's a different position, It's, you can imagine it's wiggling, like wiggling, and then there's a different. This coordinate now is different one. This length is a different one, and well, that angle is a different one. You see, every single point is a different configuration of the system, right? So, as you can imagine, when this is snapshot, so it's frozen in time. If we let it evolve, so you can see that it will change to other configurations. So, see that in this space, every single point of this curve has a different configuration, so you can see conceptually how this represents the evolution of the system as a whole, right? So this is the picture, right? And so we saw from the first lecture that this corresponds to the more coordinates than that. This represents, this coincides, sorry, this corresponds to the curve on parameter space, right? On the space of generalized coordinates. That corresponds to, say, in a straight space. So this is Rn. That's Q. Okay? So it's important to say, Q is this. So okay, Q is the surface. We don't care where it lives. It will live in a potentially, well, in this case, no, it will live in a very big Cartesian product, potentially very big Cartesian product of Euclidean three-dimensional space. Okay, so we don't really care about where it lives. We just know that conceptually, every single point of Q represents a configuration of the system, so a snapshot, different, and so these values of the parameters correspond to these points, the values of the parameters, not the actual distribution of the particles in the systems. Okay. So we see, I was trying to argue that the evolution of the system corresponds to a smooth curve. And smooth, why smooth? Why don't we require, like we can jump to here and then go back there without a connection? Well, because that would mean that particles will teleport in between points in the space, and we don't want that. We know that from experience that particles move in smooth trajectories. They don't pop out of nowhere and then disappear. Okay, so that's why we require. The very reason why we require paths to be smooth, or not smooth, but continuous on three-dimensional ordinary space, is the same argument. The same argument goes for general configuration space. There's no difference with that. Okay, so you have this picture, and so we see that the evolution of the system is a curve in configuration space. Okay, so we saw that configuration space is parameterized by the Q's in our examples. So curves can actually be described on these generalized coordinate frames just by, so we're going to take a canonical or standard or universal, whatever we want to call it, parameter t, which in principle will just be a real number, right? And the map from the line to the space of parameters, we will typically call it Q of t. And this represents, do I want to call it qt? No, sorry. The curve on the space parameters, we'll call it qi of t. And this is explicitly q1 of t over q1 of t. Okay? But if we actually consider the evolution of the system, this curve, it's, I mean, an arbitrary point q with an ordered q. Yeah, so, sorry, yes, let's call it, yeah. Q superindex I is explicitly trying to represent all the array. We can also do this, or this, okay, and yeah, but for the time being, just actually no, actually, so let's use this notation, okay, for the whole thing, right. And then without anything is the conceptual geometric thing that represents the actual state of the system, the actual configuration of the system. Okay, so a curve, so you can see that giving a curve in the parameter space or in the coordinate, in the generalized coordinate space, we just compose with this kind of conceptual map that we have in our minds, and we get actually an evolution of the system. Okay, so this is a valid construction of the evolution of a system. So this is a motion of a system. This is a generalized notion of a system. Okay. All right. So, having argued this, we only need to study curves in these generalized spaces. So, if we want to discuss what a tangent bundle is, we will see that it arises from curves in these spaces. So I will probably keep these pictures. They are going to be useful, I guess. Yes. Yes, okay. So, every single, I mean, if we have in mind the evolution of the system, then it's obvious that every single parameter has its own independent, well, not independent, sorry, it has its own evolution, right? So, for instance, the whole system is moving in a complicated manner, but, for instance, L is only doing this. It's wiggling in this direction, so L will vary from, a minimum and a maximum, will vary like that. Theta, similarly, and phi, similarly. They have a behavior that it's physically meaningful in their own right once you know what the QNs, the QYs actually are. So in this case, L, phi, and theta, whatever they are. So if we find these equations, we don't have the actual description of the motion in 3D in a fully geometric setting, but we have the gist of the motion, we have the essence, the essential information of the motion. And so if we actually compute and find equations for these variables, we will actually, and find equations and solve them, we will actually find the whole motion of the system, because then we can use this map that at this stage is just somehow conceptual, and we will give, sorry, at this stage it's conceptual, but in practice you will actually have to construct it. So you're given a particular system, say this one, you actually start with this setting, and then you go back, say, okay, can you find that angle, but you can define also that angle, or or the height, or whatever you like, as long as it's bijective with the possible configurations of the system, it's okay. And then you end up with this space, and you start with this set of possible configurations, then you end up with this space, and then you consider curves in this space that will represent curves in this space. And in a way that you will learn during Lagrangian mechanics, you will find equations, differential equations of these variables that put together and solved give you the evolution of the points, or the evolution of the q's, or obviously the evolution of these coordinates, and in turn they give you the evolution of the system. That's what we want as physicists, as analytical mechanical physicists. Okay, so we have this, okay, and then in mechanics, we know that when we do Newtonian mechanics, we know that velocity is a fundamental concept. So it's not like force that actually determines motion, it's part of the motion itself, it's part of the mechanical information of the system. So velocity, how things change, first orders, or first derivatives of